Swayam Prabha. Digital India. Educated India.
I think the point I am making here is to say that you have to actually remember what was taught, otherwise it doesn't work. You will remember a little bit today and tomorrow you will remember less, unless in some sense you revise or you make a note of what you learnt. And it is good to make notes in the sense you write down in 4 lines or 5 lines what you learnt. So you have to summarize the discussion to yourself, and it helps to keep the memory longer. Okay, so that's a very general principle which somehow I find that many students don't do, but you should do it because it is helpful for you. Okay, so now what I want to do today is to discuss some other applications of the Sandpile model to other contexts. So let us see. So one context is called, it has a long and complicated name, so first let me write down the name and then we will discuss. Okay, so it has lots of words. Firstly, we are considering a network of computers. Okay, so these computers can send messages to each other. So that's what is meant by a network here. They are communicating processors. Okay, so each processor can be thought of as one computer, but it can send messages to some other computer, and it can receive messages from other computers, and acting on those messages, it runs some program and then send out some other messages to other people. Okay, and but what happens is that this computer, it gets some message, it processes it and sends out a message after the computation is done. But it's not clear in the beginning how long the computation will take. It may take microsecond or it may take 1 minute. And once the computation is finished, it sends out a message. But the speeds of different computers could be different. And anyway, the time spent in computation can be different. So there is no common clock which runs together at the same place. So the computers are asynchronous. Okay, so you don't know the time. And they are distributed all over, in the sense everybody has their own memory, but they can get messages. Okay, so now these kinds of things of course are well known, they occur everywhere. Internet is some such thing. And nowadays what people do is they have some program and they send it to some cluster of processors, and then they collect the answer and then you get the final answer. So the calculation is divided into parts and different people do different parts and then you put them together. Okay, so that is understandable. But now what happens is that often it is needed that I want to do some calculation, but I am waiting for input from some other computer, right? Because my calculation requires an input which I haven't yet got. So I will wait until I get that input, right? So in fact, in many clusters what happens is a lot of time of the processors is just spent in waiting, because they are waiting for input from somebody else. And if one of the processors is slow, then all others can be very fast and it doesn't matter. They keep on waiting until they get the right input. Okay, so there are bottlenecks in these kinds of stuff and they should be sorted out. But there is a bigger problem. The problem is this. There may be a computer here. It gets a message from some guy here and it gets a message from some other guy here. Okay, so he gets different inputs from different other people and the order in which these messages come can be different. Maybe this one comes before this one or this one comes before this one, right? Then if it acts on the first instruction and then acts on the second, or vice versa, acts on this instruction and then acts on this one, you may get different answers, which may not be what you like, or which may be what you like, depending on the problem. So for example, suppose this is an airline reservation system, and I book a ticket, they give me a ticket, the next guy books, say sorry, it's all full, right? So in this case, the answer of the calculation depends on the order in which the different inputs come. But there are other calculations in which I would prefer, then the answer doesn't depend on the order in which the inputs come. So for example, I may want, I want to file my income tax return. This guy also files his income tax return, right? But I don't think my income tax return should be processed in a way which depends on whether he has filed it or not, or what the outcome of that event. So I might want that the answer of my calculation does not depend on the order in which all these other processors are working. This is a very general feature of my calculation I would like to do. And so what I need is a proof in the beginning that the answer does not depend on the order in which I do the calculation. Now these proofs are usually very hard to ensure in the beginning, or they are put in at the level of design of networks or some such thing. So how can I ensure that the answers are independent of the details of the order in which various processors occur? That's the question. And one possible answer for this is that if I can ensure that this single processor, it gets message S1 and it gets message S2 and it outputs some message S3 and S4, okay? The output of this computer does not depend on the order in which S1 and S2 come, and this is true for each of the nodes. Then it is also true for the full network. Okay, so that is very simple, and the testing of this is done at each node. If I can ensure this property at each node, then it is true for the full network. Okay, so that is where this property, abelian property, comes in. It says so the way we imagine is like this: there is a processor and there is an input stack. So the input stack looks like this. There is one message here. So whenever a message comes, it goes to the input stack on the top. And then this processor is doing something, then it needs input, then it takes the message from the input stack. The height of the stack goes down. If it wants an input and there is nothing in the input stack, it just waits until the input comes. Right? So that is straightforward, it's not a problem. And then it processes and gives the output. Okay? So in the input stack, how will I, suppose there are 5 messages in the input stack, how will I choose which one to act on? There is a protocol you just define. You have to define a protocol to tell the computer which message will you pick up. It can be, there are different protocols, last in, first out, last in, first out, first in, first out. Okay, so it says that this message came in first, this came in second, this came in third. That's how the messages are stored. Then I will pick the lowest one, or I will pick the topmost. Whichever you make the rule and act accordingly. And then if you are given this protocol for operating how the stack works, then you can check if this property holds or not. If this property holds, it is called the abelian property. If it doesn't hold, then it is not called the abelian property. Okay, that's simple. Now, unfortunately or whatever, it seems like the Sandpile model is not adequate to describe this complicated system, because the messages in Sandpiles are very simple. They are just 1-bit messages, either a particle comes in or doesn't come in, right? So now we are generalizing the Sandpile model to the case where the simplest variation is that the grains come in different colors or shapes, and the toppling rule depends on what is the color of the grains which are there now. If it says if there are 2 red grains, then topple. If otherwise, wait until 2 red grains come and only then topple, or some such thing. You can make your own variations depending on the problem, but it is possible to have more than one type of grains. Then in these messages, typically there is an identifier which says that this message is coming from this computer, right? Then I know that, I am doing this calculation, x plus x2, x3. There is one message x1, one message x2, one message x3. Suppose I have only got x1 now, then I wait until I get x2 and x3. Once I have got all of them, then I need to know which to multiply and which to add, and that will be coming with the identifier to the message. Okay, and then everything goes through, there is no problem. So the Sandpile model can be modified, at least conceptually, to include these variations, and at least at the conceptual level, the proof that the answer will not depend on the order reduces to the case that at each node you can check that this abelian property holds or not, and if it holds, then it is good. If it doesn't hold, it is you write some other protocol. You write your programs in a way such that you get the result you desire, right? So I might have to add extra identifiers to my message, or do something or the other, or change the protocol of handling messages or whatever it is. Okay, so that is an example of a much more non-trivial application of the Sandpile model. Okay, and now I will just give one more application and then I will stop. And so this application is with river networks. Okay, so what's a river network? So usually what happens in rivers is that there are small rivers which join up to form bigger rivers, and these rivers join up to form other rivers, and so on. So if I look at some, I don't know, that's a river network. Okay, and so I try to draw here qualitatively the Ganga Yamuna network. This is Yamuna, Ganga, and this is Ghagra, and this is Chambal river, and some such thing. No, just qualitatively. But you can go to the map and you can make lot of these networks. But very interestingly, one property of river networks is that, yes sir, yeah, louder. Mic is not working, okay. So this is the problem, plus Oh, now it's working. Okay. Whenever it stops working, you tell me again. Okay. So what happens is that when we draw a river network, typically people draw some rivers and they don't draw smaller rivers. So what happens is that rainwater comes on the ground and then it goes into small rivulets, nalas. They join up to form bigger rivers. We join up to form bigger rivers and so on and so forth. So when you make a map, you decide on the smallest river you draw. River is measured by how many cusecs of water per year. If it is less than 1 million cusecs, I don't draw it. Right? So, Ganga will be drawn, but some other tiny nala entering the Ganga will not be drawn. Okay, so that is the way we process river networks. But anyway, when people draw the river networks, they have been studied for a long time. And what people found is that there are some phenomenological laws about networks which are true for different networks. You can take the river network for Ganga or Sindhu river or the Amazon river or the Missouri river or something else, the Lena river or some such thing. And most of these river networks have some common properties which are independent of the particular river. Okay, so what are these common properties? Okay, so firstly, there is the notion of what is called the rank of a river. Okay, so if I have a river which starts at the top, okay, so it is called a rank 1 river. If two rank 1 rivers join, that is called a rank 2 river. Okay, when two rank 2 rivers join, it is called a rank 3 river, and so on. But if a rank 1 river joins a rank 3 river, then it is still called a rank 3 river. Okay? Yeah. Yeah. Rank is equal to rank of maximum, rank of major, rank of the, let's just write it in words. I can write a formula, but let's not bother. If the two rivers of the same rank join, then the rank of the new river is the bigger by 1. If it is not the same rank, then the maximum of the two is the rank of the resulting river. Yes. So in practice, more than 2 rivers don't join exactly at the same point. So this question you can ask in principle, but in practice what I will do is I'll just imagine that this river joined a little bit later and use the same rule. Okay, so I think in experimental situations it's not an issue. Okay, so what people said is that you can do this thing with some rank of a river. So, there is this Bhagirathi and Alaknanda, these are some 2 rivers. When they join up, it is called Ganga. That's a higher rank river, it has a different name sometimes. Okay, but Ganga is going, then one Nala joins. Then I don't change the name of the river, it's still called Ganga. So that's the general idea which is continued here. Each rank characterizes a particular river. If 2 rivers of some rank join, then you think of it as a different river. Okay? So now there is a very interesting law which is called Horton's law. It says, so if you take a big network of rivers like this, sometimes you can have thousands of streams in a network. In fact, you can easily get Google map and you can look at the network of Mississippi River, even Ganga River, and it will have thousands of rivulets, lots of nalas go and join up the river. So each of them is considered a separate stream and the number of streams is very big. Then you can say how many of these are streams of rank 1, how many of them are streams of rank 2, how many of them are rank 3 and so on. And those are numbers which are specific to a given network, right? And so it says number of streams of rank R divided by number of streams of rank R plus 1 is independent of R. Okay. This ratio of number of streams of rank R and rank R plus 1 is a bigish number like 4 and it is roughly independent of R. If you write down these numbers N1, N2, N3, they will go down in a geometric progression. Okay, that is an observed law and it is interesting why this is true, or can we understand why it should happen theoretically. Okay. There is another law which is called Heck's law. The Heck's law is defined like this. So you take this river network, you sit at some point in the river. Okay. At this point in the river, you can calculate the flow of water coming out of, as it is, how much water flows out. Okay. And then from here, I can go upward and I can go here, or I can go here, or I can go there, upward. And let me take the longest upstream. Okay. So it says length of longest upstream. It's a variable. For each point in the river, I can define this quantity, right? And I can also define the drainage area. Drainage area is how much water flows in here. Okay. So the model is that there is a flat landscape, nearly flat landscape, and rain comes in roughly at constant rate on this landscape per year. So let us take yearly average, and then all the water which comes in here has to go out, okay, and goes into the sea. So the sea is over there, so this water will find some way to go to the sea. How does it decide which way to go? It goes into, let us say, the steepest descent or some such thing. It has one particular direction in which it goes, and then it joins with something else and then goes further. So here, I didn't draw these streams before, but now I am drawing. Those are the small streams which I forgot to draw before. But the flow here comes out of all the water which come in from all this area. Whatever rain comes in this area will flow out at this point. So that is called the region of drainage, right? And this flow is proportional to the area of the drainage region because the rainfall is uniform nearly. Okay, and so this one says that drainage area will become bigger if the stream is bigger. If the stream is small, then the drainage will be small. but this is a length and this is an area. So I guess this should be a power 2. Turns out it is not a power 2, it is like a power like 1.6. So that's a surprise, how come that the area doesn't scale like the length squared, right? It needs an explanation. And so what we will do is we provide with a simple model which gives you an explanation for some such phenomena. Okay? The model will be simplified, it will not be fully representative of the real thing, but at least it provides some understanding of how these kinds of laws occur. Why should it happen that these numbers should go like this? Okay? So what we will do is we will construct a simple model in which you will prepare a drainage network like this, and we will show that these laws hold in that model. Okay, and then you can of course see that if that model is applicable to the real world, maybe, may not be, but at least we can try. Is this point clear? The idea of this simple model is precisely this, that you see some phenology, these are these kinds of laws, and I want to make a model in which these laws are seen. And that model is realistic, it doesn't sound stupid. Okay, very good. Okay. So the model is defined like this. I have a flat landscape, nearly flat, it's a very small slope, and let us draw it like this. So the area is represented by points. So I don't draw continuous areas, I just draw localized regions. This point can be thought of as a small square like this. All the rain which comes in this region is called the rain coming at this point. It's called discretization of space. Okay? And so I imagine that there is a flat landscape in which there are points which are drawn in this way, and a uniform rainfall occurs in all this land. So every point gets 1 unit of rain every year. Okay? And now this water has to flow out over here. So this is the sea, and this water flows into the sea. Okay? And let us say there is a gentle slope down. So the whatever rain comes in here, it can flow down either to the left or to the right. And I don't know the local geography too much, and it's kind of random. So we'll say that it randomly, there is a direction assigned to each site. It has an arrow which says water from here will go in this direction. Okay? That's the model, and all directions are equally likely. That's my model. So now this water will come in here, and this water may also come in here, and whatever goes out here will be the inflow from here, and there is 1 unit which comes in here, and all that flows out. Okay? So if I draw the outgoing arrow from each vertex, so I have a lot of vertices, from each vertex there is an outgoing arrow direction downward, but which way down I am not sure. Then what I have, then I have a path to all the way below. From each side there is a unique path to go down, that is the river, which the path followed by that water, which rainwater which comes in here, will use this path to go down. So if I draw this fully, you get a graph like this. and so on. Okay. So this is called so the claim is that in this graph, since every site will only flow down in one way, you can never form loops, right? So there is no loop and all the sites are covered. So this is called a spanning tree graph. It will go through all the sites, it will be tree-like in the sense it won't have any loops, and so it's called a spanning tree graph. Spanning tree, and it is a directed graph, so it's a directed spanning tree. Okay. So now the model is the end of the definition of the model. It's a, if I give a geometry, then you can construct a graph on this by assigning the direction of arrows. And now I am taking a random realization of that construction, and I am asking properties about this, the system I picked up, one realization. And so what can you say about the properties of this randomly picked network? Turns out that you can pick your favorite sample from this system, and I will pick mine, and some properties are roughly the same in all of them. Okay. And what are those properties? That is the common property of a randomly drawn sample. Okay. So it turns out that, for example, I can ask that, okay, there are some sites in which there are no incoming arrows. Okay, because this one the arrow is that way, this one the arrow is that way, so this one has no incoming arrows, right? So it has only water coming from the rain, and the outflow is 1 unit. Okay, and for the moment we will consider each bond as a stream. So I can ask how many streams have flow value 1 in this big network. Okay, and so the answer is easy to work out, and I will tell you the answer in this case. You say, look at this site. What is the probability that this arrow is not pointing this way, it's pointing this way half? What is the probability that this arrow is also not pointing in this way but that way, it's also half, and these are independent. The probability that none of them is pointing is 1 by 4. So with probability 1 by 4, this site has no in arrows, and so outflow rate will be 1. Okay, so it says fractional number of sites with outflow 1 it's a bit surprising, you know, you can be very deep down, but still there will be sites with outflow rate only 1. Okay, and then I can ask similar thing for site 2 and site 3, and make a statistics of this number with outflow rate, number of, and flow, sorry, flow first and number later, flow number of streams. 1, 2, 3, 4, 5 table, and see how these numbers vary with the flow rate. Of course, with bigger flow rate there are fewer streams, but can I tell what will this number be, at least in this model, right? The answer is this calculation can be done, and it will not be done here now, but you can read about it if you feel sufficiently interested. And I gave the indication, I did it for flow rate 1, but suppose I want to calculate what is the probability, what is the fraction of sites which have flow rate 2. So how can you have a flow rate 2? This site should have a flow rate 2, means that something should come in here with rate 1 and this will have 1 coming here. So this should not come and this should be empty. So nothing should come here, nothing should come here, right? And this one should be directed somewhere else, so nothing should come here. So it's a similar calculation, you say that these bonds should not be present, this bond should not be present, this should be present, this should not be present. And this one can go down this way or that way, doesn't matter, you will get f equal to 2. So I will not do this algebra here, but you can see that for any such finite 2 or 3, you can find out all the configurations for which this is possible, and you can write down the probability of each of them and then add them up and you get your answer. And interestingly, what happens is that these calculations are exactly the same as the directed sandpile model that we studied before. Because these kinds of configurations where this thing goes here and this thing goes here and then stops are similar to what we did there. So in fact, it's one-to-one correspondence between the corresponding counting problems are the same. If you have actually solved what is the number of graphs with probability of toppling equal to 7, you will have a corresponding answer for this case. What is the probability that f is equal to 7? Okay, so the problems can be converted to each other, and in this model, you can show that this power here, this one is actually 1.5. You can calculate this number theoretically. So I can see that okay, non-trivial powers can appear, and okay, in the real life it is not 1.5, it is 1.6. So it has a different explanation. So the model is not fully there. And the explanation is that in these strings are very downward. But if I allow for strings to do this kind of stuff, then maybe the answer changes, and perhaps it does, and that is you have to put in the extra physics that the real system is not exactly like what I modeled in first stupid model, then the answer can change. But some lessons we learnt in the first problem still are useful to understand river networks. This problem is very different. I wouldn't have thought that sandpile model will be useful in understanding rivers. Because, here the stuff is that rivers join to form bigger rivers, and in sandpiles the picture didn't look like this, no? At least the original model didn't look like this. But if you change variables and you think about it in some particular way, then the problems actually become equivalent. Okay? And there is another point which let me just mention, that here what happens is that this thing goes and goes to the sea. So there is no stopping. But in the sandpile model, the key point was that the avalanches stop after some time. So how can these problems be related to each other in any way? Right? So the answer is that instead of thinking about going down, suppose I reverse the direction of time. I start here and go up. Then after some time I will stop and I will not be able to go anywhere further up. And then the problems become more similar. Okay? So you have to, you have to be inventive, you have to be able to imagine some different situation, you have to make some correspondence which is not obvious a priori, but then it is useful as an understanding tool. And the details of all this stuff can be found in some. So there are some lectures I gave at ICTP in 2019. So you can look at them. They are actually longer lectures. These are some 9 hours of lectures instead of 2 hours. And you can watch them at your pleasure. You don't have to watch them now. They are available on the internet. And There is a review article which was written in 2006. So I only write this much. I don't remember all the details of the journal and volume and page number, because those you can find from the search, right? So I will not do all that. And then let me stop here. I am happy to answer any questions you may have. Okay. So I will wait for 1 or 2 minutes and then I will go away. So in this model, the rivers are drawn as lines, but actually the rivers have a width, and the rivers down here have a bigger width than rivers up here. Okay, so all those details can be included in a more accurate description. But it is good to have some simple model which doesn't have all that detail inside it, because it still tells you something, and it tells you something in a way which is not hard to understand, and then you can add the details as needed. So this is not the final word on river networks. You can do much more, but that requires much more work. Okay. Yeah.
There's something called artificial neural networks. How is this concept applicable here, or is it because I think that's how because everything is connected with each other into this.
Yeah, no, so very good. So she has mentioned the word artificial neural networks. And what is the connection of all these sandpiles to neural networks? And the answer is that I don't know too much about neural networks, but there are some neurons which fire. And once a neuron fires, it sends out some chemical to another neuron, which then fires. And so you can imagine that there are avalanches of neuronal activity. Okay? And so, this kind of sandpile models, also there is the threshold dynamics, that a neuron gets messages from chemicals from lots of other neurons, and only when the total chemical strength of incoming signal is big enough, then it starts firing. That is the typical model. And so in that sense, it's like a sandpile model, and a suitable variation of the sandpile model in which you take more than one neighbor, and the threshold is 1000. Once the number becomes more than 1000, then it topples, and so on. So then those models can be studied. Okay. Yeah, I think lot of complicated things happen in the real brain. Okay, and it is not very clear that suppose I'm thinking of something, and you put in all kinds of electrodes in my head, and you measure the neuronal activity everywhere. Hard work, but suppose you did it. Will you know what I'm thinking about? Not quite clear. All the ECG signals today cannot tell you what you are thinking about, no? Even if you made them 30 million times better, it may not happen. Sometimes they say, oh no, this area is lighting up, so it means that you are thinking of something related to languages. That's too vague. It's not enough for me, you know. So I think one can learn a little bit about the neural networks from analogy to Sandpiles, but maybe the most interesting questions there are not related to the kinds of things which are interesting in Sandpiles. When I'm when I'm thinking of brain, I'm saying that in the dumbest case, I'm thinking of what should I do next? How will that show up in the signal, in the neuronal activity? I don't know. Okay. Okay.
Thank you, Professor Deepak Dhar, for your lecture on the applications of the Sandpile model. From abelian asynchronous distributions to river networks, we really enjoyed your lecture. We realized how natural phenomena like sandpiles and river networks to avalanches and earthquakes are all interconnected, and from solving one small problem like sandpile can solve multiple similar problems in the real world.